we have a presentation from Willem Klumpenhouwer. And it's my great pleasure to introduce my former colleague today. Willem did his undergrad in theoretical physics at the University of Guelph. And then, what did you do in between your...
Bunch of random little things.
And I did a bunch of random little things. Came to the University of Calgary and started, did a master's at the same time as me and transferred into his PhD, and now works at MTO in a completely different area than his thesis was in. But I'm very interested to hear about his thesis because I know next to nothing about it.
Thank you, Jason.
You're welcome. Thank you, as always.
So I'm Willem. I'm going to talk today about my thesis topic. I can mention briefly some of the stuff we're doing at MTO. There is some, we do connect with different researchers occasionally, but I'm going to focus mostly on my my thesis research, which I sort of colloquially titled The Unpredictable Bus. Seems to be a good way. My supervisor was Chan Weerasinghe. So that's why his name's up there. I am currently employed at MTO. My title is planner. Functionally, my title is data head. So just decided to use the word data head. I work at the Systems Analysis and Forecasting Office, so there's a lot of modeling, provincial-wide models, Golden Horseshoe model you may have heard of. We do a lot of GPS analysis. We do a lot of work with some congestion analysis and a lot of sort of traffic-related data work. I've also written, it's a little dormant now because it's Calgary-focused, but I like to write and try to make transit, specifically public transportation issues, but transportation issues in general, easier to understand and bring up issues from sort of a clear, logic-oriented perspective. So, I do some writing there. I have a PhD in transportation engineering from the University of Calgary. For partly what you're going to hear about now, and as Jason said, a Bachelor of Science. So I'm going to give you a brief overview of the sort of thesis problem that I was challenged to solve, and then I'm going to talk a little bit about the Markovian Bus. There was somebody here that was very excited about the word Markovian. So we'll talk a little bit about the Markovian Bus, this model, briefly about optimization. And I will hopefully have time to give you a little demo of some software I wrote to work on this, and then talk a little bit about future work, as one mostly does. And if you have any questions that are burning in your mind, you can put your hand up, and I'm happy to call on you, or you can write them down and save them to the end. I like to keep things pretty casual. A little more nervous today because these fine officers over here are here to make sure I don't say anything negative about MTO. Just kidding, that's not true at all. So feel free to ask questions, throw stuff out. So today we're going to talk about I'll call it a bus route. Functionally, it can be any transit route, really. It's not technology specific. We're talking about a single bus route, so we're not talking about a network of buses. And we've decided that by some policy or another, or some other type of optimization, we've already decided where the stops are going. We have some sort of scheduled headway, so it's a scheduled service, not an even headway service. We're talking about a schedule. So the headway's already been decided, which is the dispatching policy. We have some information about some boarding and lighting patterns that we're going to have to incorporate. And we have some information about how the bus is moving between stops, either from GPS or what I ended up using was timestamps from an automated passenger counter, which gave me both passenger numbers and time. So buses, I choose the word bus because they're the most random. I maybe should use Streetcar here in Toronto, but buses are unpredictable, they're random. This is an example of data from 2015 on one of the longer routes in Calgary Transit, and how often it was more than 1 minute early was eventually the policy they set counted as an early bus, or more than 5 minutes late. So you can see buses are fairly random, and as they progress along the route, they get more random. So sort of a general background as to why we might want to deal with random buses and what we might want to do about them. And there's a strategy that gets used by a lot of transit agencies to keep buses on track. And it's a fairly simple one. You just come up with a schedule, you come up with some average runs, And then you pick certain stops. Sometimes it's all of them, sometimes it's a few of them, and you call them time points. And you make the rule that if a bus is early at that point, so you have a scheduled time for it, and if it's early, it has to wait. For the other stops, the buses will tend to just carry on, regardless of whether they're late or early. And you can build in some extra time above, say, the averages to at these stops to sort of have more buses stop and wait. And so the advantage is that a bus at this time point, if it's early, any early bus will leave on time, exactly on time. And if you build in some extra time, buses that are running late are able to sort of catch up to the schedule. Right? The disadvantage is buses will spend time at the stop sitting there. So for example, the really simple example is the GO trains all have time points at every stop because they have a specific scheduled time, so they will sit and wait if they're early. Yeah. And so how this sort of works conceptually, mathematically, is that normally you might have some sort of distribution of when a bus would arrive at the stop, early or late, early or late. So this is the average time. There's a distribution, there's some randomness, depending on how random it is, it's wider or narrower. And when you create this time point, what you effectively do is you say all of this probability of the bus being early gets converted to being on time. So you basically take all of the probability that's happening on the left-hand side and you put it all onto this spike on time. It's effectively how statistically, I guess, randomly, the time points work. And what that does is sort of increase the average, right? So you're kind of pushing buses later, but the variance, so the width gets smaller. And so you kind of have this trade-off. This is the mathematical trade-off, so you have a variance that decreases, but you're giving up speed and time. So passengers will have conflicting ideas. So if you're waiting for a bus, you want the bus to show up exactly when it was scheduled, and then when you don't want to be late, and you want it to get to your stop exactly when it's planned to get there, or maybe earlier. But if you're on the bus, you don't want it to stop for anybody else. You don't want it to stop to be on time anywhere else. You just want it to drive. So you kind of have a conflicting personality, even just whether you're waiting at the stop or you're on the bus. And so this conflict and these competing interests kind of leaves room to potentially optimize something, right? So you have a bit of a trade-off, and if you have a trade-off, you have the potential to try and find this sort of sweet spot between these two competing factors. So effectively what that looks like is that by choosing some configuration of time points, so choosing where we put them, how long we have the bus wait there, how many of the time points we have, see if we can find this optimal balance between having more control, which means longer travel time but more reliability, or less control, which means having faster travel times maybe on average, but worse reliability, which also causes people to plan around it and effectively increases travel. So, to do that, we need effectively what I wanted to create was some sort of mathematical laboratory so that I could adjust a bus route, and I wouldn't have to do it in real life. So I could adjust a bus route on the fly and see what the effect of changing different stops and different things into time points would have on the overall route behavior. So this, for example, is if you were to sit, so the sort of thought experiment is if you're sitting on the bus, and as you go to every stop, you write down a number which is the number of minutes either ahead or behind schedule it is. So 0 would be right on time, positive numbers are late, and negative numbers are early. And so if you were to do this at every stop, even if, say, you didn't stop and you passed by, you still wrote the time down, you might get something like this. This is from an actual bus run in, I think, November of 2015 sometime. And you can see it's kind of random. And it turns out that this is very similar to the kind of randomness you get, say, if you were to flip a coin every time, or roll a dice every time. And so this leads to the idea of these can be mathematically modeled using math called Markov Chains, which is a stochastic process. So I'm not sure how many people are familiar with this process, but I'll go through a little bit of how it works. But effectively, you say that each stop, a bus can have a deviation from the schedule, like an actual bus, and individually buses are quite random, but collectively they form this distribution, and they follow a sequence of stops. So you kind of have this version of time. Usually stochastic processes have time. Here we have stops as our discrete times, because really we're only interested at what the bus is doing at each stop. That's where passengers interact with the schedule, basically. So the idea is to model the bus as a Markov chain. so discrete time and discrete states. So how does that work? So here's an example. So let's suppose that buses are governed somehow by this law that of a 6-sided dice, right? And so at every stop, as you're departing, you roll a dice. And if you get a 1, the bus will run faster than normal, faster than average. If you get 2 through 4, the bus does its normal thing, stays average travel speed. And 5 and 6, it runs slow, right? So let's say a bus is running fast, and then you roll, so it gets to stop 1 ahead of schedule, and then you roll an average, so you roll a 3, then you get, it stays ahead, right? It doesn't change from its current status, its current state. And then let's say, you roll a 6, and then it goes back to being on time. So this is an example with 3 different states. The bus is either ahead of schedule, on time, or late, right? And you can represent these probabilities effectively with a matrix, right? So it's called a probability transition matrix. So it's from this stop to this stop. This would be I or I plus 1. And so an on-time bus will stay on time, so O to O, if it's any of those 3 of the 6 that are average, right? So 3, 6 shows up for those. For the edge cases, effectively you can't jump from a late to early, or early to late. So those probabilities get combined. But yeah, so they're just representative of these probabilities. And then you effectively have a matrix that represents some sort of random behavior at every bus stop, which is kind of cool. And these matrices don't have to be the same. They can be different for every stop, and they will be. You can do it. And this wonderful idea of Markov chains is that you can string all of these matrices together, and if you multiply a bunch of them together, it's as if you're evolving the route as it goes along from stop to stop. So this is, for example, after 2 stops, you have the same matrix squared, this times this. You start on time, the probability of 1. And so you have a 20% chance of being, I think, early, 44% chance of being late. If you do it for 20 stops, you can see it shifts up. So buses, by the way we designed this, are running later and later. And that's effectively because we gave more probability to late than we did to early. So it should be pushing the distribution. It's effectively a drift is what you get. So the next thing is to say, okay, what does a time point look like in one of these? Well, we talked about cutting the distribution off. So effectively what we said is the probability, if this matrix represents a bus leaving a stop, a bus at a time point will never leave early. So all of the probability of becoming early has to now get added into the on time, right? So we're effectively chopping the distribution off in the same way that we talked about earlier. So we now have 2 types of matrices. We have a regular matrix, and we have this theoretical time point matrix. So if I sub that in to wherever my time points are, then it will affect the probabilities accordingly. So here's a simple example. It's those same 2 stops, right? So if we make stop 1 a time point, you see I've subbed in the matrix with the zeros in the early column, and you get a certain distribution out. And if we compare it with what we did before, you can see the probability of being early goes down. Probability of being on time the probability of being early goes up, which makes sense. Probability of being on time goes a little bit down, and late goes down again. Because we've held buses from being late. Oh no, sorry, I'm flipping them around. It should be earlier. Which is what I summarize here nicely, in case I got confused. So the chance of being early goes down, on time goes up, and late goes up. So the idea is, the whole point of a time point is to try and avoid buses from being early, or to build in this extra slack time. So it seems like we've captured the trade-off here, at least, sort of from this very simple example. But 3 states is not, buses either early, on time, or late is not a particularly realistic way. So what if instead we give every minute a number? So now if we want to say, well, the bus can be between 10 minutes early and 10 minutes late, you have a 10 by 10 matrix. And this 10 by 10 matrix will have different probabilities. So this is an example. It's a normal distribution through the middle. Whiter on the screen is higher probabilities. And so you effectively have a matrix now that represents a little more realistically a distribution of change from one stop to the other. There's a fun little thing that happens. There's these edge effects that happen on the corners because we're basically saying, well, a bus can't get any more than 10 minutes early or any more than 10 minutes late. And so all of that tail of that distribution has to be lumped into one thing. So individually that looks like a problem for matrix, but if you make the matrix big enough, the effective distribution ends up having effectively zero at the tail, so it cuts off fairly easily. So this is an example of, I think, a model after 80 stops. There's two different sort of extreme scenarios. One is you don't put any time points in, so that's what this dashed line is. And the other one is you make every stop time point, in which case, as you can see, probability is much higher in the center and it's cut off, there's no early, and it pushes the tail up. And both of those have sort of negligible numbers at the edge, so there's not this weird effect. So now we have this model effect that sort of describes, in theory, this describes bus behavior, buses evolving along a route. And now we need some way to try and capture the costs or capture some objective function so that we can try and minimize it. And so sort of building on the work that my supervisor has done a lot, we have this sort of theory of a total cost function, which is the idea that passengers contribute time and the agencies contribute money, and sort of together we put all of these costs together and we try and minimize it collectively, right? So these are the ones that are considered in this research. An early bus will miss passengers, right? If passengers arrive ahead of schedule but after the bus, that's a problem. Wait a while. There's a bus that's late, delays passengers. Bus that sits at a time point, so there's people on the bus who don't want to get off. They're through passengers at the stop, and so they are effectively giving up extra time because the bus is sitting there doing nothing for them. And there's you can build in some special circumstances. So there may be certain places where you need to transfer to a train, so there's a big penalty for a bus being late. And there are some operating costs associated, so longer routes slowing the bus down costs more to run. There's this potential that if their bus is extremely unreliable at the end, you have logistical problems with where to assign a driver next or paying overtime, so that is also capturable. But you can sort of decide on whatever costs you think are appropriate or captured to try and sort of minimize this. There's a bit of an issue though, which is that if you have n stops, and each of them could be a time point or not, in theory, you have 2 to the n possible combinations of routes. And a route could have 80 stops. The one we're looking at has 80 stops, and so that's 2 to the 80 combinations, which is an extremely large amount of things to check and effectively impossible. So some optimization, the optimization part of this got interesting. So I'm just going to briefly go through sort of very simple background of how these costs happen. For passengers arriving, so early passengers, we also have to consider that passengers don't just sort of show up randomly. Often we assume that passengers show up kind of evenly, randomly between stops, especially if the headway is even and we don't publish a schedule. But if I give you a schedule and I say the bus comes every 20 minutes, you're likely to try and time your stop. But you're not perfect either. So this was a distribution we used to show sort of how passengers are arriving. So you can see the majority of the arrivals will happen in this area. If this is when the bus is going to arrive, some people will be late, some people will be quite early. And so we can use that to figure out if a bus is 4 minutes early at a stop, or 2 minutes early at a stop, it'll pick everybody up here, it'll miss all of these passengers. And that's effectively what the math shows. This is just the area under the curve between the number of passengers that are missed. This is them having to wait an entire headway. So they have to wait. If you miss a bus, you got to wait for 20 minutes. This is a cost associated with waiting. And then this is the probability of that occurrence happening. And then you just add up all the probabilities, you get an expected cost. Do the same thing for late buses. Same idea. They have to wait just a few minutes extra. They're inconvenienced in that way. You can also introduce, I didn't mention, the idea of this slack time, this extra buffer time. So we chopped off at 0. You could add in some slack time. You can chop off at 2 minutes later, and all that does is just shift where where you're putting your time point. So it'll change the probabilities, but it's the same idea. Through passengers only wait at stops that are time points, otherwise it's sort of regular operations. And so this is a flag to say whether there's a time point or not, there's a cost, there's a number of people on the bus that are going through, and then this is again the probability, the amount of time they wait and the probability of that occurrence. And last but not least, the transit operator has a cost, so there's a basically a sum of all of the extra time they would have to wait at each of these time points. And then you can add a penalty if you want for lateness at the end of the stop. Great. Any questions so far? I'm going to do some more like pretty picture demoing stuff.
Why the bus that goes only a few stops?
Sorry?
80 to 100 stops is
Yeah.
a lot.
Yeah, and I'll show you. We did a couple of.
Tried 10 stops, 15 stops.
Right. Yeah. So one of the things I did do was, can I just make up a bus route that's really short, that's nice and clean, so I can play with it. I did that a little bit. There are some quite short routes, and I have a couple of examples in here as well, that you could sort of brute force. But 10, 15, it starts to where at least with my code is where it started to get a little out of hand. I'd have to leave it for several days or whatever. So I did do some, and I found actually that the results I got from using the algorithm I built seemed to not be that much worse than just doing it and finding the absolute perfect answer. Now that was for short routes. I don't know if the situation applies long. Yeah. So there's sort of 5 routes going on at once here that I looked at. There's an east-west. This is Calgary. It's very faded in the background. This is Calgary. The dashed lines are the LRT system that we're so proud of. And there's a north-south long route, Route 3, an east-west through the downtown, Route 1. There's this sort of semicircular route, which doesn't exist anymore, which is Route 20. And there is, I also looked at a BRT route, which has a bunch of skip stops. And BRT in Calgary is really skip stop service. And then I did one very suburban route at the very top, which is also quite short. So in order to do this, I decided to put together a little bit of software to help me sort of play with this, because trying to figure out how to optimize this in a heuristic way meant that I need to figure out what happens. I want to be able to play with a route and see what happens. So I built this little piece of software. So if we pick, Route 1 is fine. You can put in all the parameters, which is all the stuff that I talked about earlier in terms of different distributions. And then it will go through and just, again, using the data that we have, using the standard deviations and the means of all of these travel times that I've collected from Calgary Transit was kind enough to basically provide me with 3 months worth of bus data for the whole city, both GPS and APC. So I was able to get distributions and then create theoretical distributions and then use that to build these matrices. So it's putting together a bunch of matrices, and then it's going to do some plotting, and then it's going to be done. Right. So then it sort of puts together some of the cost components. So this is using the values of time that I had and using the values of time that we pulled together and the various operating costs. This is $15 per run of a bus for one route. So there might be, 16-hour operating days at 20-minute, even 20-minute headways. It's a lot of buses, right? So it can add up for the sort of total cost. And then remember, this is passengers and operators together. And you can see that so this one clearly has a lot of variance right at the beginning. So there seems to be some departure variance going on. And then you can see that the standard deviation sort of grows over time, which is very similar to that plot I showed you at the very beginning. The randomness of it goes up, and so there you also have this drift going on between the mean and standard deviation. And then you can simply pick. So. Look for. Probably should have picked a shorter route. So this shows all of those different cost components, right? Cost of an early bus, late bus, cost of a through bus, cost of operating. Right now, there's no time point set, so the extra cost due to slowing the bus down is not, it's all zero. But you can see here, okay, well, stop 36, 38, which happens to be downtown, has this huge spike. And it's due to the fact that there's a lot of people getting on and off, and the fact that downtown has a lot of lights, a lot of turns, a lot of stops, and so it's fairly random. So you figure that might be a good place for a time point. And so basically I did this, and then I tried to turn it into an automated process. And so I said, okay, well, let's find where these spikes in the costs are, and sort of work your way through. So now the scale has shifted significantly. Cost has dropped by about $1. And you can see we have some operating costs now here and some cost to through passengers. And so now I'm going to look for the next spike and say, okay, well, that must be the next sort of potential problem area, and we'll work our way through. Yeah? So that's effectively the algorithm I developed, was to do it this way. And it relatively fast. And it did not need to check all 2 to the 80 stops, which is good. And so here's an example. Here's an example of the sort of, what is this, the standard deviation that the model spits out, which is the orange line on my screen, the brown line actually on your screen, and the blue dots are sort of actual sample data from the route. So without sort of calibrating it really, other than to say that I used some of the descriptive statistics to create a theoretical distribution, which then created the model, it's relatively close. It follows at least the pattern a fair bit. And so I actually ended up doing 2 different algorithms. As you can see, one didn't work. One was just to split the route in half and find the best spot, and then split it in half. At that point, do it again, this sort of recursive idea. So Calgary Transit's on the left, again in brown, and that's sort of their existing things in terms of a cost. Now, of course, the cost that Calgary Transit might be trying to optimize might be different than what I have, but nonetheless, this is what they had. They didn't do too bad of a job. If I had shown no control at all, it would have been much, much higher. And then this first algorithm I did, this divide and conquer algorithm, and then this peak one, which I just showed you. And so you can see there's some significant cost improvement. And it also tends to do it with fewer time points overall, except for this one route 3 here, which is one of the longer and busier, it's the longest, well, it's the busiest route and one of the longest routes. It has a lot of some of the most variability. But in either case, the peak finding one seemed to do it with less time points. Now the BRT route, it flipped. So the BRT route is number 306, and for that one I decided every stop should have a time point, which is apparently how they do it in Germany. And so there's the nice thing about cost optimization and trying to solve this problem of where to put these time points. That was the core sort of problem. But the model really can do a whole bunch of different things, which is really nice. It's a little bit separate from the actual optimization part. And it's, so you can use it as a basis for simulation, which I'll talk briefly about. We looked at bus bunching. I'm working on right now sort of seeing if I can have it work for a network, so you can sort of get a bunch of routes at once and see how many missed transfers are there between routes, and what's the reliability of having buses meet up where you pick a hub, say a university, and you say, okay, how many people are missing their stops because of unreliability, and is there some optimization that can happen there? And I'm imagining there's other applications, especially with the simulation, that we can get to as well. So bus bunching is very common. I imagine you've heard of it before. Streetcar bunching, because I searched for streetcar bunching, and this is the first thing that came up. But common occurrence in streetcars, but also a common occurrence on buses, where there'll be a big gap of time, especially when buses are running close together, and then a whole bunch of them will come at once, right? And effectively this happens because if there's the first bus gets delayed or thrown off a little bit, it will, on average, pick up more people if it's running a little slow, and that will slow it down more because it takes time, a little bit of extra time to pick up more people, and then it'll make it even more, and even more, and even more, so it'll slow it down. And the following bus or streetcar will have less people to pick up because the gap between it's slightly smaller. And so it'll run a little bit ahead of what it normally does. And then that means it'll pick up even less people, and et cetera, et cetera, et cetera, until they start to form pairs, or pairs of pairs, or pairs of pairs of pairs, I think, in this particular instance. This might be a cheating photo because there might be a car here that's disabled, but yeah. So, one of the things I looked at was to say, okay, can I use this Markov chain idea, this sort of model of a bus, to simulate buses moving along a route? So effectively simulate a bunch of buses and see, so for buses that deviate, you figure out how many passengers it picks up that are extra or are fewer, and you record a sort of wake that it leaves in terms of passengers, how many extra or fewer passengers it might leave, and then the bus that follows it has to handle those, and it also has its own randomness. And so you can see what happens. So for a completely uncontrolled route, this is, I think, 500 trajectories, sort of just simulated 500 trajectories. I had the buses all start on time, as you can see, and you get this really cool spread that happens. Some of these buses get way off, right? Way early or way late. And I said, and this was this is the difference in time between the two buses. So if they started, if the headway was 9 minutes, if they got to be, the difference got to be 9 minutes, that means they've effectively reached each other. So this is where the buses would be officially bunched. So I said, okay, well, let's just see how many times this line gets crossed. A rough estimate. If you add in the time points, you can see the effect that happens, right? So you can guess probably just from looking at this graph where I've placed on this stop, where I've placed the time points. Basically where it starts to pull the distribution back together. And you can see there's far fewer trajectories that end up sort of going over this threshold of bunching. So even just by trying to optimize these time points, again, so this is also the number of passengers that are left behind. Again, 35 is downtown, lots of activity going on there. But this is with no control, and then this is with control. So you can see there's a lot fewer passengers that are get on the wrong bus, a bus they didn't intend. And so effectively, it's the same idea. How many percentage of the buses got bunched? And you see Calgary Transit tends to do about twice as good as doing nothing, or half as much as doing nothing. And then the algorithm I found also seemed to show that it was half as much. So this has no cost component to it. It was just a matter of, does this decrease the idea of it? So it's an example of a simulation. Same idea. It's the standard deviation of the separation. How much variance is there between the two buses, or do they stay exactly 10 minutes apart? And that also gets decreased with trying to add better control. So sort of this chapter was sort of a bit of an externality of trying to do the optimization process, which is nice to see. Yeah, so I already mentioned extending this to try and look at some network reliability and try to improve this software that I've been playing with to actually maybe see if a transit agency would want to use it. And always trying to find better ways to optimize things that are kind of not brute force. That's it. Thank you. Any questions? Yes.
Okay. Markov process is not the only one.
Yeah.
And there is queuing theory. There is Poisson arrival times. And maybe you want to compare and complement this study with this kind of processes.
Yeah.
And then, to be practical, in case of bunching or any trouble along the line, maybe the drivers can be allowed to do some flexibility or local decisions that will make much more sense than in the extreme case of bunching, which is very costly.
Right.
So we may recommend different.
Sure.
Like for the planners, the easiest thing to do is any time of the day, I have fixed schedule, and I have 3 drivers, 2, and they just go uniformly.
Right.
This is very clumsy, and very like first cut,
Right.
ignorant way. So,
Yeah, so there's sort of two things you mentioned there. The first one was about other stochastic processes and other approaches. Now, you can use a Poisson process to create a Markov process. A process is Markovian when each section is independent. So there's an assumption here, which is to say that there's no overlap or no interaction between the distributions between stops. That there's independent, and that effectively the future is only dictated by the present. So effectively a bus says, well, it doesn't matter if I'm 5 minutes late, it doesn't matter how I got to be 5 minutes late, the next step I take is really only going to change whether I'm 5 minutes late or not. It doesn't matter the path I got to being 5 minutes late. So that's an assumption that's built into that. And so the Poisson distribution is also a stationary process, but there's a lot of different ways. My grand supervisor, Newell, supervisor, kind of started the ball rolling with this by trying to make it infinitely. He did a very physicist thing, which physicists count 0, 1, infinity. That's how we count. And so he did an infinitely long bus route. All the stops were the same. Everything was uniform. And he tried to sort of figure it out. And he got some very complex stochastic differential equations that he never really ended up solving. And he said it's much more complicated than this. And so I kind of went the other way, which is to say, is there sort of a practical route for that? The second thing you mentioned was about, well, in a way, real time, right? There's no consideration here to real time. This is sort of a medium-term planning decision. Effectively locating time points sometimes needs some physical work. So sometimes you need to have a bus bay or have something. You can't necessarily stop a bus in the middle of the road, although you can. Like, it's really a policy question. But there's also something to be said for using this in real time, which is to say, why not update where I'm at? And I say, okay, well, if I start 5 minutes late here, what's the rest of it going to look like? Should I wait? Should I not? What kind of adjustment should I make? So you can translate this to calculate, to try and figure out in real time whether you should update what you're doing. Change your behavior, either tell the bus driver to drive differently or have it hold. There was a paper done with a bus loop. It was every 5 minutes, I think it was an even headway, and they had a grad student with a phone with an app built on it, and he stood there, and every time the bus pulled up to his stop, he would tell the bus, okay, based on where the other buses are, you're going to wait 3 minutes, you're going to go. And he just basically redispatched buses, and it made things way better, just a grad student on his phone. Don't say that grad students can't do it. But yeah, and then you do the same thing. You say, well, what if I could give all of the buses power to do that all in real time? And there's some math surrounding that. That tends to focus on trying to keep buses in an even headway, and scheduled service can be a little bit trickier. But I do think that there is an application for using this in real time.
So, can your model be used to identify slow or fast drivers versus rush hour constraints?
Yeah, if you had sort of a trace related to, yeah, you'd have to, that would be a little bit more, that's a little bit less sort of this larger model. The other thing with this, again, because you're making these sort of, a time point doesn't change based on what time of day it is. At least that was the policy of Calgary Transit. Is we've decided this is a time point. It doesn't matter if it's AM, PM, night, whatever. This is a time point. And so you have to take the average day, the average bus, right? But I think you could tease out a little bit, well, what does this look like only in the AM and only in the PM? And, in theory, you could say, okay, are there any drivers specifically that are on the outlier of what's an average thing? But yeah, that would be, I think it would be really hard to find what is noise, right? What is just randomness from the street and the weather, and what is randomness from the driver? Hard to say.
Well, the title was Unpredictable Bus.
Yeah.
Can we make it predictable?
That's a good question. So you could also, I guess, also use this to, in theory, predict or do some schedule prediction too. So you could update the probability, project. There was some work done at UC about, we did some surveys about how you would like to have your data, how information was presented to you about your bus. Do you want to say it's 2 minutes late? Do you want it to sort of overestimate, underestimate? Do you want it to give you a confidence interval? The average person doesn't really know what to do with a confidence interval. So, but personally, I would love it to say, the bus is going to be here in 5 minutes, plus or minus 2 minutes. do with that, with the standard deviations this, you can do with that as you, however risky you are, you can decide how you're going to go. You got a question?
Yeah, thanks for the presentation.
Hey,
I worked at a co-op where the bus stop was a time point, so I've actually given some thought to this, but obviously not at this level. It's really cool to see you working on this stuff. You sort of touched on this in the last question, but I was hoping you could give like an indication or your vision for how something like the software you built could be applied in a transit agency.
Well, I mean, ideally it'd be great if somebody would just hire me to sort of do a reliability audit and I could tell them what to do. Because there's a lot of number crunching that goes on in the back, right? And I think like when we presented this to Calgary Transit, they're very interested to know how they're doing on average and how, and they really want to know some trends. Are we doing them, because they tend to space their things evenly in time, every 10 minutes. They're like, every 10 minutes we'll do a time point, and then plus or minus a stop given whether it's feasible or not. And so they wanted to know, is that too many? Is that not enough? And the answer is there's more nuance to it, right? That, 10 minutes on a super unreliable stretch is very different than 10 minutes in a nice separated lane that's covered, that runs, priority signals, etc. So I think I'd love to be able to sort of demo this kind of thing to people, and then it's a matter of, as with most projects that involve a lot of real world data, 80–90% of the work is trying to figure out how that data works and what are the weirdness about it and how to get it to work. So that's working with individual people. They all have their data in different ways. They've hired some different contractor to do it differently, so a lot of that comes out of it. But it would be really nice if people, I had this written up in a paper, I got Calgary, I guess it's the Star now, the Star Metro. Somebody did a piece on me about this, and he got a quote from a counselor, and the counselor says, well, it's just, it's great in theory, fancy math, but, who knows if it'll work in real life, but you have to try it first. Right? So it'd be great to do like a pilot route somewhere. If anybody knows anybody at City of Toronto or TTC that wants to sort of throw dice with the bus route, that'd be great for a year. Any other questions? Yeah.
In your analysis, was there any difference in weekdays versus weekends, like more reliability during weekdays?
I didn't get into that, in part because I had this sort of thing at the beginning, which was I had to take this average bus, period, for the whole, I guess they update these every 4 months, schedule-wise. There definitely would be, and there definitely is a difference in weekend, and the service type is different. They changed the schedule to try and make up for the fact that, let's say there's less boarding and alighting, but they don't change where the time points are, and that was really the focus of the question. So I don't have like a graph showing that variability, although I'm sure I could find that, and it would be the case. And we've seen it, and you see it everywhere.
The software, but the demo was excellent.
Oh yeah.
It's so easy to, drop down those parameters, the cost, and then get those visuals.
Yeah.
Is this custom made? What's going on in the background?
Yeah, I built that myself. It's all but from scratch. Yeah, and I had a little bit of experience with some GUI programming, like I've used that before. In Guelph, I built some data tools for a group that has an instrument on the Mars rover, and they wanted to find a way to catalog some of their calibration data. So building some of the database stuff I had done before, but I decided it would just be easier to do that and be able to play with it and actually see what's going on. And then there might also be payoff at the end, which is that there's some actual piece of software that thankfully people can think looks really useful. So, yeah. Yes.
I have a question.
Absolutely not.
Okay. So you make a discrete time assumption. I'm just wondering, during the initial phases, if Chan had any trouble with you making a discrete assumption? Because I know he's a big fan of continuous assumptions. And
that's more about handling your supervisor than it is about.
But did you explore any?
Yeah, so we did, and I started puzzling out, trying to see if there's some continuous way. There was some previous work that looked at this in the 90s, also through Chan, and they focused on some more continuous things, but it started to fall apart from being this implementable solution pretty quickly, right? And so there's two parts of the discrete, right? There's the discrete time. There's discrete time and discrete state. So I decided that bus schedulers probably don't care much more than the minute, although you could in theory do the exact same thing and make whatever number of seconds or intervals of 30 seconds. Yeah, you could look at intervals of like 30 seconds at a time or whatever, so that could be changed to be a little more continuous. But it was also the fact that we had this paper from Newell that tried to do things very continuously, and it got pretty murky and quite unrealistic. And he even said, well, even he said in the paper, if we're going to try and make this more realistic, it's going to take a lot more. So, and Newell was pretty brilliant. Also a physicist in transportation.
Does anyone
Anything
else?
Thank you. Thanks for your question.